Hello, everyone. I hope you're doing well. My name is Zenan Wang. I'm from JD.com, Silicon Valley Research Center. Today, I'm going to present our work on data experimentation with delayed feedback. Our product using this approach has already been launched, and we're currently drafting a working paper. So hopefully, by the time you see this presentation, it will have been uploaded to archive online. In a short experimentation, by adaptive experimentation, we're referring to the multi-arm bandits, which in contrast to a classical A/B test, will dynamically change time and probability to each treatment group during the experiment based on the realized outcome. So naturally, there's a challenge extending the bandit to work with delay response, because at any given time that the bandit is making that decision, some feedback may not be realized yet. So in this talk, I'll present a method to solve such a problem. As far as I know, we are the first one to propose and implement such a practical solution for this problem. So here's the outline of this talk. We'll start by with motivation and problem statements. Then we'll talk about some examples to illustrate the challenge. After that, I'll introduce our methodology. Then after that, I'll illustrate our methods through some case studies and the simulation results. Finally, we conclude this talk. So multi-arm bandit has become very popular for online experiments because it's faster and more cost-effective than A/B testing. It's more cost-effective because we don't have to worry spending too much resource on non-effective treatments such as in the A/B testing cases. However, most of the bandit application focus on metrics and immediate feedback, such as click-through rates, and will fail with delay feedback, like conversion rate, CVR. But the CVR is more relevant and useful in many cases because it's more closely related to the revenue. So our problem is to extend the bandit application to metric with delay response. And the core challenge facing us is that the delay distribution needs to be learned during the experiment. In the next few slides, I will talk about why do we need delay distribution and what are the challenges estimating it. So in this talk, we will focus on the conversion rate. It's a metric that is very important to an e-commerce company like JD. Here, we define conversion delay to be the time between an ad click and its conversion. In the graph on the right-hand side, we show the density of conversion delay for the same SKU, but with different creatives and audience. Audience here means the type of the user. So for some type of user, we can see they convert very fast, but for some other types, they convert much more slower. And for some creative, some pictures, they also convert faster. It makes sense because for some picture, they could say, you have to act now in order to get a discount or something. So what's the takeaway from this is, even for the same SKU, the delay distribution is different across ads, creative, and audience. Because every time you change the environment, you change in treatment, the delay distribution could be different. So the delay distribution needs to be estimated during the experiment and for each experimental group. Okay, now how does the delay distribution help us? So first I put the naive CVR here. This is a formula people use in industry. The problem is it's a total conversion divided by total clicks. The problem with this is that at the time, anytime you compute CVR, not all the conversion is observed yet. So the naive CVR will naturally underestimate the real CVR. We can see this in this example on the right. In this little experiment, we have a real CVR equals 0.5, and assume that the conversion is always delayed by 1 hour after the click. So to, for example, to compute the naive CVR at T2 here, we can add, we'll add all the orange bar as numerator and divide by all the gray bars as denominator. So clearly it's underestimating, and this shows in the red line. One way to correct this is we use only gray bar from T0 and T1 and omitting the T2 gray bar, then we can get an estimate of CVR equals 0.5. The reason we can do this is that none of the clicks from T2 has any real chance to generate a conversion at T2 because we know it would be delayed by 1 hour. So this should not be included in the denominator. So that is the general idea of this CVR2. That is we have a numerator is still using total conversion, but divided by effective clicks. For more general cases, general delay distribution, let's assume we have delay distribution indicated by tau, then we can define the effective clicks as a weighted sum of clicks, and where weight is based on the probability that the conversion is realized since the click until now. And what that means is the more recent clicks will receive much less weight, just like we illustrated here. Okay, so we know the naive CVR is biased, but you may think that biasness doesn't matter. It's not that important as long as we can identify the best treatment. Here's an illustration to show why that may not work using the naive CVR. So here we have 3 groups, and each group we have a different CVR and a different delay with different means. And here we assume the exponential delay is exponentially distributed. What this graph shows is that when the delay distribution is different across group, using naive CVR indicated here as a red line, we may not even identify what's the best arm or best treatment. But using a delay corrected version, the green line, we can. So naive CVR can be bad. Okay, in this slide, we'll discuss the challenge in estimating delay distribution. During the biggest challenge we have is during the experiments, the observed delay is rest sensitive. What that means is, for example, if we want to estimate at t equals 1,000, we'll only observe conversion delays smaller than 1,000. For simplicity here, we'll assume all the clicks happen at 0. It doesn't change anything. But then for the clicks that have at T1000, for the clicks that has now converted, there are 2 possibilities. Either they will never convert, as indicated by the red portion here, or they will convert, but will in the future. For traditional analysis to work, all the events that a sensor need to eventually happen, which means that we need to exclude the red portion. So how do we exclude? Then that means we need to know what the real CVR is. We got ourselves a chicken egg problem. We want to know CVR, but in order to get CVR, we need to know the delay distribution. But in order to get delay distribution, we need to know the CVR. To solve this, we use expectation maximization method. Intuitively speaking, we'll start with some initial guess of the CVR. Then we can guess what the red portion is. Then we estimate the delay distribution. Then we update our guess of the CVR and the red portion. Then we repeat the whole thing until everything converges. Okay, here is how we formally implement the expectation maximization. We'll do this for each experiment. In our application, we assume the delay distribution is exponentially distributed with the parameter lambda, because it matches our data quite well. But in theory, this whole procedure will work well with other delay distribution as well. So to begin with, we have some initial value, lambda 0 and theta 0. And we enter the next step that's called E step. In this step, we'll assign weights. For each click, we assign weight based on the W. W is the probability of the click will generate eventual conversion given the observed conversion. This should be a yi. And the elapsed the time. So we can write for our cases with extended distribution, this is wi. With that, we go to the next step, M step. Here we take wi, the weight as given, and we'll maximize this likelihood function. This is actually very simple because it has an analytical solution. Okay. Then we can repeat the EM step many times until convergence. After that, we'll get some estimate of CVR. Okay, so how does this our whole system work? So this slide shows the how we integrate EM procedure with the bandit and how the whole system will work. We'll estimate CVR for each group and the delay distribution for each group as we described. After that, we can use that as input go to our bandit algorithm. The bandit will use a delay correct CVR to compute assignment probability. Then if it meets stopping rule, then we'll stop the experiment and declare the results. Otherwise, we'll continue. The user will be assigned to groups based on the assignment probability, and will collect their click and purchase log information. Then we go back to the cycle. We update our conversion rates, estimation, etc. Then we update the assignment probability. So for our application, we found the Thompson sampler bandit works the best. I'll show you some results in the next slide. Okay, so here are a few simulation results comparing different bandit algorithms. Here we have 5 candidates. First one is the random bandits. It just shows random results, random groups. The second one is naive Thompson sampler. Here we just use the naive CVR. There's no EM procedure at all. The third one is called delay track UCB. It's a method proposed by some literature. And here we do the EM procedure and get the delay track CVR. The fourth one is called fully Bayesian approach. Here we assume the beta prior and exponential delay distribution, and then we compute the numerical posteriors and use it with a Bayesian UCB algorithm. Theoretically, this is probably the best we can achieve. This approach is very computationally intensive, and it takes more than 10 times of the time of other algorithms. The last one is what we propose. We call delayed Thompson sampler. We use a delay corrected CVR with a beta prior Thompson sampler. Okay, now let's look at the simulation. So on the first 2 panels, we have set underlying delay distribution to be exponentially distributed. Those two are different in terms of real CVR setting. And we can see that our delay Thompson sampler works pretty well in both scenarios and on par with the fully Bayesian approach. Others not work so well in both. In the third scenario, we use a Weibull distribution as the underlying delay distribution. It's a different distribution, but still close to expanded distribution. In this one, we can see that our delay Thompson sampler still works pretty well. Also, the fully Bayesian one. In the last one, we use the criteria data to draw the empirical delay distribution from the real world data. We can see that our delay Thompson sampler still works pretty well, still pretty good compared to others. Okay, here we present the result of an actual experiment after our product launch. Here we have 2 versions of ads for a cell phone. I have a black version and a white version. It's for the same SKU, but different pictures. On the left, it shows an estimated CVR over time with a dashed line representing the final CVR after the experiment ends. What this shows is that our estimation can gradually learn from the about the eventual CVR. On the right-hand side, it shows the impression count. What this shows is that our bandit is at work and it's gradually directing more traffic to the better version. Okay, so here's more graph about CVR. Those results are from same experiment, but here we break down by version of ads, and we want to compare the delayed correct CVR, the green line here, with the naive CVR, the red line here. What we can see is that our delayed correct CVR, in general, is much closer to the eventual CVR, where the naive one, even closer to the end of experiment, is not even close. There's a gap. So this provides some validation of our methods. And okay, after that, let's conclude our talk. So in this talk, we show that there are many challenges in expanding bandit algorithm to delay response. We propose to use a expectation maximization method to estimate the delay distribution, and therefore the correct metrics or estimation module can be easily integrated into a bandit system, and we propose to use a delay Thompson sampler and show that it works pretty well. Okay, so if you have any questions or suggestions, feel free to contact me at wangzunan5@jd.com. And lastly, we're hiring. So if you're interested in working on similar topics like this, feel free to contact me as well. Thank you.